Welcome back. We are doing section 1.3, which is actually the last section in chapter 1 out of our coursework here. And then we will move into chapter 2, which kind of gets the start of calculus, the basic kind of very foundation of that. So our last section of review in chapter 1 is dealing with trigonometry. Okay, so trigonometric functions. And this is going to be a review of a whole lot of stuff that we go over in trig. So again, you need to make sure that if you're not up to par with some of these concepts and such, that you get with me or you work on your own and go through some Khan Academy stuff. There's some stuff in your book on the study sessions that you can look at on my lab math. It's under the AR section of, I believe, symbolizing for a review. And so you can kind of work through some of those problems as well. So if you need any help, let me know. So the first thing that we're going to look at and remind ourselves is about radian measure and trigonometry. Calculus typically requires that angles be measured in radians. So a lot of times in trig, we like to work with those degree measures, but trig, we don't really work with degrees. We work with just radians, okay? So working with a circle of radius r, the radian measure of an angle, we're going to call it theta, is the length of the arc associated with theta, denoted by s. So s is the length of the arc, theta is the angle, r is the radius of the circle, okay? Divided by the radius of the circle, which is r. So in trig, we usually are working on the unit circle, which has a radius of 1. Therefore, on the unit circle, the radian measure of an angle is the length of the arc associated with theta. So we don't have to worry about that different r, because whenever I associate with 1 most of the time, then it is just kind of kicking back the same thing for our identity property. And so recall to change from degree measures to radian measures and vice versa. To go from degrees, like 180 degrees, to pi, what would we do? Well, you have to multiply by pi over 180. So I have to end with a pi on top is the way I remind myself. And then to change from radian measure to degree measure, you won't be doing this much, but just as a reminder, you have to get rid of that pi. So we're going to take 180 and divide by pi. So that's how you would go back and forth between the two. Now, there are some common radian measures that we will deal with, and this is where you were working with some special angles when you went through your trig course, and so I'm going to kind of work through these from 0 to 180, but we will not only be restricted between 0 and 180, we'll go on around that unit circle. So, we're looking at the degrees. I will write each one of the degrees for the special angles from 0 to 180. We have 0, 30, 45, 60, 90 gets me on that y-axis. 120, 135 has a 45 degree reference angle in the second quadrant. 150 and 180. So if we take each one of these and change to radians by doing what we were just saying up here, multiply by pi over 180, here are the corresponding radians for these special degrees. We have pi over 6 for 30. We have pi over 4 for 45, pi over 3 for 60. The way I remember it is you have to have a 3 and a 6, a 3 and a 6, so you can't have double 6s or double 3s. Pi over 2 is going to be my 90. Then we end up having a 2 pi over 3. This is the 60 degree angle in the second quadrant. Then we have 3 pi over 4, 45 degree angle in the second quadrant. And 5 pi over 6 with a 30 degree reference angle in the second quadrant. And this is equivalent to pi. So make sure that you know your special angles. Make sure that you can take some trig functions of those special angles. And we'll review that here in just a second. Standard position is important because that's kind of what gets us on the coordinate plane and gets us orientated there. So suppose that I have some point xy that is on my circle. And angle theta is in standard position if its initial side is on the positive x-axis and its terminal side is the line segment, call it OP, between the origin and the x-axis. Hang on just a second. The origin, excuse me, and not the x-axis, from the origin and P. I'm off a line. Now, an angle is positive if it is obtained by going counterclockwise from the origin, don't forget, or from the initial side, the 0-degree angle, which is along the x-axis, to counterclockwise rotation from the positive x-axis, which is also the same as the 0 degrees. Now, if I draw a picture of that, for instance, if I, which I'll do here, well, we could go ahead and do that. If I have this coordinate, here is your initial side. This is the initial side. This is also corresponds to 0 degrees here, or 0 radians. So if I start there and I travel some angle measure over here into the second quadrant, it is going to lie on the circle. We could say that this is a radius 1 if I want, but let's create a circle here. Not saying that this is the unit circle, but if it is, it would have a radius of 1. If I look this, I'm going to change colors here a little bit. This is what we're going to constitute as theta. And it corresponds to this point P, comma, xy, where this distance would be the x, and actually that would be a negative x, and this distance would be the y value. And so you're corresponding there on that. So the reference angle that I was talking about is this angle right here in that second quadrant. So remember, everything kind of stems from that. But to get to that angle, you have to start from 0 and go counterclockwise. Now, if this is, in general, we're not doing a unit circle with a radius of 1. If these are my measurements in general with an x and a y, I can actually find this hypotenuse by doing a little bit of Pythag. Now, that hypotenuse is also the radius of my circle, so that's why I'm going to do r squared. So if I want to get r by itself, then I would just square root both sides, and the radius is equal to the square root of x squared plus y squared, and that's that piece in my circle that is right there. Okay, again, we got a little delay here. But that is r squared. Again, if it is a unit circle, then each one of those sums squared underneath that square root would have to equal 1. All right, now, there's another thing, a lot of things that we have to do. This kind of over here, this picture alludes to what we're going to work with in a right triangle. That was probably the first trig that you encountered, was right triangle trig. One should remember the right angle or the right triangle ratios. Sometimes we refer to that as SOHCAHTOA. That's the way I always used to teach it. So if you have not been taught that way, remember the S stands for sine, and that ratio is the opposite over the hypotenuse. C stands for cosine, and that ratio is the adjacent side, which is the next to side of the angle. So I always like to refer adjacent as the phrase next to. Then the T here represents tangent, which is the opposite over the adjacent. That is the ratio that you have there. Remember, with any trig function, it does not make sense to have a trig function without an angle. So you have to have sine of some angle equals opposite over hypotenuse. Now, each one of these are reciprocals. We mentioned that in the previous section. Reciprocals of each other. So the reciprocal of sine is going to be cosecant, which is down here. The reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. Okay, so make sure that you know to reverse those or do the reciprocal of that. So for secant and cosecant, remember an S and C starts with here, a C and an S. They can't be double C's or double S's. So remember that those are opposite. Okay, so you might have some cases, and we'll see some where we have to do some of that right triangle trig. Now we get to the unit circle. And so the unit circle, this is kind of the same as my picture that I have up there. Here are all our special angles around. We're going to start at 0 and go around to like 135, going counterclockwise. Remember, each one of these radii is equal to 1. So if I take kind of this triangle, drop down the perpendicular, and I work with this triangle, notice these are my points, x and y. So if I do x squared plus y squared, that's going to give me r squared. The radius squared, and in this case we would end up with a 1 for r because we're on the unit circle. So the unit circle is nice to know. I would by no means memorize all of this. I know that some teachers teach kids to do that. I am not one. I like to know the first quadrant. and also do some special right triangles to remember my ratios. I am not a big memorizer of that whole thing, but you do have to remember also that on this unit circle, those values are very important to the special angles that we have. For the special angles in trig, the unit circle is helpful when determining the trig values. Remember, the ordered pair gives the values of cosine of theta and sine of theta for each angle in the unit circle. So, for instance, if I'm here at 150, which is 5 pi over 6, that's the angle. This is the reference angle. That's a 30-degree angle in the second quadrant. This negative root 3 over 2 is the cosine at 5 pi over 6. And this is the sine at 5 pi over 6, which is 1/2. So they do correspond. You just have to remember. But again, by no means do I expect you to memorize that unit circle whatsoever. This is the way that I always kind of use it. Just kind of giving you an idea here. In reality, one does not have to memorize the full unit circle. One can know some special angles and a particular mnemonic device, and all can be well. So, for instance, with the special angles, as long as you know that reference angle that you're dealing with, if it's a 30, a 60, or a 45, and you figure that, just as a small little review here, the reference angle, again, is found by dropping the perpendicular here, and from the x-axis up to that point, what is that angle? In this case, it's a 30, okay? If I drop the perpendicular here, this reference angle up to that point, that's a 120-degree angle. That would have a 60-degree reference angle. And that's important when we go and find these values, okay? So, using the special triangles. So, there are two 30, 60, 90 right triangles and a 45, 45, 90 right triangle. So you should have learned these in geometry. As a review, these are the numbers I like to see on there. For a 45, 45, 90, it is an isosceles right triangle. So we have legs of 1. If we use Pythag, we can prove that that is the length of square root of 2. And if I have a 30, 60, 90 right triangle, it can be proven. Let's say the shorter leg is 1. The ratios, you can multiply by 2 to get your hypotenuse, multiply by root 3 to get your 60-degree side, which is the one across from the 60-degree angle. And so if you remember these two triangles, then if I say, well, what's the cosine of 60 degrees, then using right triangle trig, your SOHCAHTOA, that is the adjacent over the hypotenuse. So we would have 1/2 as the cosine of 60. If I would say, well, what's the cotangent of 30? Well, cotangent's ratio. Tangent is opposite over adjacent, so cotangent is the reciprocal. So it would be the adjacent over the opposite of the 30-degree angle. This is the next two side over the opposite, so that would be root 3 over 1, or just root 3. 45 degrees, they're pretty simple, okay? Now the kicker is sometimes they're positive and sometimes they're negative. So that's where this little mnemonic device comes into play, because that's going to give us the signs of each one of those according to where the original angle lies. So in a 4-quadrant coordinate plane, we have all students take calculus. Some people use classes. I always like to say calculus. That's the way I was taught. So what does this mean and what does this stand for? The A stands for all trig functions are positive in this quadrant. Every single one of them. The S stands for that the sign is positive and it's reciprocal. So the reciprocal of sine is cosecant. Those are the two trig functions which are positive. Everybody else is negative. For the T, that represents for tangent, and its reciprocal, which is cotangent, are positive in the 3rd quadrant. And for this one, last one is cosine, and its reciprocal, which is secant. Remember a C and an S. Those two trig functions are the only ones that are positive in that quadrant. Everything else is negative. So when you are going through and finding special angles or trig functions of special angles, then you can use these. So we're going to do that here in this exercise, these next ones, okay? Sine of 2 pi over 3, I need to know the exact value of that trig function. So we're not using our calculators, we are figuring this out, knowing that I have these triangles, knowing the unit circle if you want to flip back to do the unit circle, if that's the way that you've memorized it. But I think this is easier. You'll see me a lot of times write this on the board or write this on my paper so I can visually see that and do it pretty easily. All right, so 2 pi over 3. If you like to use degrees, recognize that that's a pi over 3. That's going to be actually a 60-degree angle. So I have a 1 pi over 3, a 2 pi over 3, and here we get 3 pi over 3. So we're looking at this angle right here. It is in the second quadrant, and I'm looking for sine. Sine in the second quadrant is positive. Well, now I refer to my special right triangle here, and I figure out, well, what is the sine of a 60-degree angle? Right triangle trig tells me that the sine is the opposite over the hypotenuse. So, from SOHCAHTOA, you have to write that up here so you can see that as well. Please do that. So, the sine of a 60-degree angle, opposite over hypotenuse, that would be a root 3 over 2. We know that it is in the second quadrant, so therefore sine is positive. Root 3 over 2 is your answer. Now, what's the cosine of 5 pi over 6? So, where's 5 pi over 6? I always gauge here from like 0 to pi over here. This is 6 pi over 6 if I'm working in the 6's, so I know I have to be between 0 and 6 pi over 6 somewhere for 5 pi over 6. So, we're going to get 1 pi over 6, 2 pi over 6, 3 pi over 6 would be that pi over 2, 4 pi over 6, and 5 pi over 6 actually gets me that 30-degree reference angle in the second quadrant. So, we're again in the second quadrant. Cosine in the second quadrant is negative. Now, we go to our 30, 60, 90 triangle. I'm looking for the cosine of a 30. Cosine is adjacent over hypotenuse. Here's my 30. Where's the side next to that? It is root 3 over that 2. So negative root 3 over 2 is your answer. Okay? If you're a pro at this, work these through and then go through and find my answers. You don't have to watch the whole thing if you already know how to do these. All right, so tangent of negative 5 pi over 6. Well, 5 pi over 6 we just talked about, but this time it's negative. So that means instead of going counterclockwise, I'm going to start from the 0 and go clockwise. 5 pi over 6 is going to be this guy over here, 30-degree angle now in the third quadrant. So that means that tangent in the third quadrant is positive. Therefore, my answer is going to be positive. Now, again, this is a 30-degree reference angle. Reference the number in the bottom. Think of it as pi over 6. That's your 30-degree angle. So I need the tangent, the opposite over adjacent of a 30-degree angle. The opposite over the adjacent would be 1 over root 3. Now, it might, I don't know, you might have to rationalize this in order to get the correct answer in my lab math. Not sure if they'll take 1 over root 3. Most of the time we leave our answer in rationalized form, which would actually be root 3 over 3. Okay? Tangent of pi. Where's pi? Pi, well, here's 0. 180 degrees is going to be this guy right here. Now, a lot of times when they're on the axes, I like to look at the ordered pair. That is the ordered pair of negative 1, 0 on the unit circle. So tangent is the same as opposite over adjacent, but it's also the same as, if you look right down here, the sine over the cosine. So remember, the ordered pair is the cosine sine, so if I do the sine over the cosine, that means I'm 0 over negative 1, which is actually 0 for my answer. Okay, so again, a lot of information in just one section. This should be somewhat reviewed. These are going to be the crucial pieces that we need to know for calculus. All right, now, 11 pi over 3. 11 pi over 3. If I go by pi over 3s, this is 0 pi over 3. This is 3 pi over 3. This is 6 pi over 3. So this is one that I have to keep going. I'm going to have multiple revolutions to where I can find this angle. So this is 6 pi over 3, and I'm adding 3 pi over 3 each time. So this is 9 pi over 3. That means I need 2 more. Because if I get to over here, that's going to be 12 pi over 3. That's too much. So that must mean I stop in the third quadrant, or the fourth quadrant for this 11 pi over 3 angle. So if you have to go multiple times, please do so. All right, cotangent. Is cotangent positive or negative in the fourth quadrant? Notice here cosine and secant are always positive there. Therefore, this one has to be negative. And I'm looking on a pi over 3 reference angle. So what's the cotangent of a 60? Tangent is opposite over adjacent, therefore cotangent is adjacent over opposite. So of the 60, where's the adjacent side? This is the opposite, this is next to, so it would end up being 1 over root 3. which is the same as what we just saw 2 problems ago, negative root 3 over 3, when you rationalize. Okay. All right, let's try secant of negative 9 pi over 4. Big thing is where is negative 9 pi over 4? So every 180 degrees is going to be 4 pi over 4. So here's 0. I'm going negative, so I got to go clockwise this time. This is going to be 4 pi over 4. This is another 4 pi over 4, which is 8 pi over 4. And I need to go one more, which is going to be 1 more pi over 4. So we are in the 4th quadrant. What do we know about the secant in the 4th quadrant? It is positive. It is a reference of a pi over 4, or a 45-degree angle, and secant is the reciprocal of cosine. So cosine is the adjacent over hypotenuse, so the reciprocal would be the hypotenuse over the adjacent. So choose this 45, choose that 45, it doesn't matter. This is going to be the hypotenuse, this is the opposite, and this is the adjacent according to this angle right here. So I need to go the hypotenuse over the adjacent, so let's go root 2 over 1. Which I'm just going to write that as root 2. Now again, you don't have to write the pluses if not. I'm just writing them down to start with. All right, and our last one, cosecant is the reciprocal of sine. Down here on this little chart, maybe I should have put this at the beginning. 1 over sine is that cosecant. So I need of 2 pi, and it's positive, so I'm going to go all the way around that unit circle 1 time. That again is another axis point at 1, 0. And remember, I have to do 1 over sine. Well, in an ordered pair, this is cosine and this is sine. So I need to now do 1 over sine, which is 0. Well, 1 over 0 cannot divide by 0 ever. So therefore, this we refer to as being undefined. So it's okay to get undefined answers. Those things happen, and make sure you don't get confused between having a 0 or an undefined, because that can be tricky. If it's 0 over 1, it's definitely 0 like we have here. But if it is ending up 1 over 0 or any other number over 0, that is undefined. All right, so here's some trigonometric identities that you should have worked with. One that's really, really important is this guy right here. Now, do you have to memorize everything on that? Not necessarily, but you can prove from here to get the other two, and that's what I like to do on my paper. To get this guy right here, to get a cosecant, that means I need a 1 over sine. So I can take this and I can divide by sine squared of theta each time. And this is how I prove to myself what the next two are. So this becomes a 1, this becomes a cotangent squared, and this becomes a cosecant squared. So I get the other one. Now, if I don't want that one, and I want, let me undo. If I want the third one here, I need a tangent. Well, that means I need to divide this by cosine squared, because tangent is sine over cosine. And if I divide everything else by cotangent squared, I can prove to myself that I have this third identity where this is tangent squared plus 1 equals a secant squared. And so we can work with that. So hopefully you were taught that. If not, there's your information for today. New information, but that is going to help us in some cases where I know there's a lot of memorizing to do. You don't have to memorize that as much. Now, of the double and half angles, I believe this will be important, the sine of 2 theta, and this one possibly. Maybe this one, but we don't work with that one as much. Definitely that sine squared. We don't see that too much, but it's possible. And so that gets us kind of the double angle formulas within there for that. Okay, so be familiar with those. These are the identities or properties that are true for all angles in their domain. There are other trig identities, but these are the most common. All right, moving into solving some trig equations. This is going to be helpful within our work in calculus, so here's our review for that. When solving trig equations, one is looking for the angles which make the equation true. So that means we're going to have to know those special angles and be able to work with that. Sometimes the domain is restricted and sometimes it is not. So for our first two examples, we end up having a domain that is not restricted. Here I have a domain that I'm going just from 0 to 2 pi, so one time around the unit circle. But hopefully you remember that these functions are cyclic, so it means that it could have the same value for multiple angles. So we have to account for that, and the way we're going to do that is to add on like a 2 pi k or a 2 pi n, okay, where k or n are integers, okay? So the idea of solving this equation, we want to get the trig function by itself in this first one. So if I want to subtract 1, I get the square root of 2 of sine of x equals a negative 1. Then I'm going to divide by root 2, and I get negative 1 over root 2. Now this is also the same as negative root 2 over 2. So there's going to be 2 spots on my quadrant where sine is going to be negative. All students take calculus. Well, it's definitely not going to be in the first and second quadrant. We are going to be in the third and fourth for that sign to be negative. Now the question would have to be, and this is where you need to be familiar with your special angles, where is the sign negative 1 over root 2, or where is the sign just root 2 over 2? That root 2 comes from one of those 45, 45, 90 degree angle triangles, okay? So if I have 1 over root 2, that means I've worked with that 45 degree angle to get the, the opposite over the hypotenuse for the sine. So we're working with a 45 degree angle here, but what quadrants are we in? We just said it had to be in 3 and 4. So if I need this 45 degree angle and I need this 45 degree angle, we need to know what those are so we can solve for x, okay? So from the x-axis, positive x-axis of 0 degrees to here, I'm working in fourths. So this is 0 pi over 4. This over here is 4 pi over 4. Well, if I go one more, that means I add a pi over 4, so that means I'm at 5 pi over 4. And a way to remember this, if I get all the way around, that's going to be 8 pi over 4, but I don't need all the way around. I need one less than that. So from here to here, this should be a 7 pi over 4, and you can do that by subtracting pi over 4 from 8 pi over 4. So if I was restricted between 0 and 2 pi, those two things would be my answer, but I'm not. It's going to occur every time I go around. Well, one time around my unit circle is equivalent to 2 pi. So that means if I'm at 5 pi over 4, when I go 2 pi more around, then I'm going to have another angle at which our sine value is equal to negative root 2 over 2. So the way we work with that is that we go ahead and just add the revolution, add the 2 pi, k we say, or 2 pi n, where k is a member of the integers. So it could be positive, it could be negative. And I'm going to do the same thing here for 7 pi over 4. So it occurs every revolution around. K is a member of the integers. Now I've seen it where there's an n instead of a k. But that right there would be your final answer. Okay? Now it works with, you got to watch with the period. Or sine, cosine, secant, and cosecant, then you're going to have a period of 2 pi. But if you're working with tangent or cotangent, then that plus would be a plus pi k or a plus pi n, because it happens every 180 degrees that it repeats. Okay? All right, let's try this guy. 2 pi cosine of theta, or excuse me, 2 theta cosine of theta plus theta equals 0. And we need to solve for theta. Well, there's a whole bunch of thetas within there. First, though, within these two terms, notice that they each have a common theta. This theta here is by itself. That theta also is. Now, remember, this is all one entity, so you can't separate those. I'm going to go ahead and take out these two thetas. So factoring using trig functions is going to be important, and it's something good for you to see that. So if I take this theta away, I'm left with 2 cosine of theta. Plus, if I take that cosine or that theta away, I'm just left with 1. Is equal to 0. So, what do I know? I now need to set each one of these equal to 0 because I'm dealing with this factor and I'm dealing with that factor. So I get theta is equal to 0 here when I just set this factor equal to 0. That's nice, nothing to solve there. But then I have 2 cosine of theta plus 1 equals 0. So I have to end up solving that equation as well. So if theta equals 0, well, that's going to happen let's see here. No, that one doesn't have a trig function. It's just theta equals 0. That's my variable equals 0. But on the next equation, it is going to occur at every 2 pi because cosine is equivalent for every revolution around that unit circle. So I'm going to get cosine by itself by subtracting 1 and dividing by 2. So I hope that's okay that I do it all in one step. That cosine is equal to negative 1/2. Now I turn to my little chart. Where is cosine going to be negative? Cosine is going to be negative. It's positive in these two. So that means we're looking at working in the second and the third quadrant. So I need this angle and I need this angle. So from here to here and from here all the way to that final position. All right, so what kind of angle, what kind of special angle has cosine being 1/2? So if you have to, go back to the unit circle, or I'm going to go right up here. Cosine is the adjacent over the hypotenuse. So here's the 1/2. Well, it is adjacent to the 60-degree angle for the adjacent over hypotenuse. So it's a 60-degree reference angle here. So what is that? Well, this is 0. 60 degrees is pi over 3. So this is going to be 3 pi over 3, and that's going to be my good little reference here. So I need this angle that's right here from here to here, but I'm minus a pi over 3. So 3 pi over 3 minus pi over 3, theta can equal 2 pi over 3 plus the 2 pi k, because it happens every time around, and theta, my other angle on this side from all the way from here to here, I'm at 3 pi over 3 at 180 degrees, and I have to add one more pi over 3, so that gives me a 4 pi over 3 plus the 2 pi k to get all the way around. Now, I like those. Yes, that's good. Most of the time I like to see whenever the restricted. That's kind of giving us infinite number of answers. Now we're looking at what is the finite numbers from 0 to 2 pi, including 0 but not including 2 pi, because that wouldn't give us a function if they were both included. Then what is our answers? All right, so here we have cosine squared within our problem of theta. And so we want to make sure that we get the trig function by itself. That's kind of the easiest thing to always try to do first. So I'm going to get cosine squared of theta is equal to 1/2. Now, I don't want cosine squared, so if we had like x squared equals 9, we wouldn't leave it as x squared. We would square root both sides and get x equals plus or minus 3. So remember, when you square root both sides, on the number side, you get two possibilities. A positive root can work and a negative root can work. So if I square root this side, I'm going to square root that side and give me a plus or minus that root 1/2. And so doing a little bit of radical work on the right side, square root of 1 is 1. I would get the square root of 2 on the bottom. So when I rationalize, hopefully you are good with seeing that as root 2 over 2. And the square root of cosine squared is just going to be cosine of theta. Okay, now I need to know what reference angle gives me the cosine to be root 2 over 2. And I need all of them. I need all the positives and I need all the negatives. So this right here doesn't really matter. I need to get one in every quadrant. So if I go back up, what is the root 2 over 2 for my cosine? Same as 1 over root 2. 1 over root 2 for an adjacent side and a hypotenuse, that would have to be this angle. It is my 45-degree reference angle, okay, which is pi over 4. So I need the pi over 4 angle in the first quadrant, the pi over 4 angle in the second, the third, and the fourth, okay? So theta in the first, that's the easiest, is pi over 4. Now remember, this over here at 180 degrees from... Get a delay from here to here, that's 180 degrees. With the reference angle of pi fourths, we get that to be 4 pi over 4. So this is 1 pi over 4, this is 2 pi over 4, this one is 3 pi over 4, or think of it as taking 4 fourths minus a pi over 4. So 3 pi over 4 is what I want. Then I'm going to take 4 fourths and I'm going to add a pi over 4 to get my angle that's in the third quadrant. So 4 pi over 4 plus 1 pi over 4 is 5 pi over 4. And this, in terms of fourths, this is 8 pi over 4 to equal 2 pi. I need this one in the fourth quadrant, so I need to back it up by pi over 4 by subtracting 8 pi over 4 minus pi over 4 is 7 pi over 4. And that gets me all the way around one time, and I'm done. I don't have to worry about it anymore, okay? Because I am within a restricted domain from 0 to 2 pi. Okay? All right, very good. So our last equation deals with a double angle. So that one could be a little bit tricky because you have to modify your domain in terms of 2 pi, okay? So for our domain, let's kind of let this piece stand out here, change our color. If this is from 0 less than or equal to pi less than 2 pi, then I need to figure out what 2 theta is restricted. So in this compound inequality, I need to multiply this by 2, that by 2, and that by 2. So that means that for this problem, I'm going to figure out all of the answers for 2 theta that are between 0 and 4 pi. So that means I got to go 2 times around my unit circle to figure that out. Now, first thing I want to do is go ahead and get this trig function by itself. So isolate the trig function. This time we're going to divide by the outside 2, or the 2 in front. Gives me a negative root 3 over 2. Okay. All right, so where is the sign negative first off? Well, the sign is positive 1 and 2, so that means we're down in 3 and 4. So I need this angle and I need this angle in the third and fourth quadrant for sine of 2 theta to equal negative root 3 over 2. So to have the sine, the opposite over the hypotenuse, to be root 3 over 2. Here's root 3 over 2 for the opposite over hypotenuse. So that is opposite of the 60-degree angle, so opposite over hypotenuse. It is a reference of pi over 3. So we need the pi over 3 angle here in the third quadrant. Well, if this is 3 pi over 3, that means I need, this is all the way 3 pi over 3, add one more 3 pi over 3 to get all the way to that ending side. So therefore 2 theta this time. So this is all of my angles. So 2 theta would have to equal, wait for the delay, sorry about that. So 2 theta has to equal, this is 3 pi over 3, add one more is 4 pi over 3. All the way around would end up being a 6 pi over 3. So I need to back it up and give me a 5 pi over 3. So those are in the first rotation around, but we have to go from 0 to 4 pi according to my domain here. So let's go all the way around one more time. Well, all the way around in a 60-degree angle is 6 pi over 3. So if I'm at 4 pi over 3 and I need to add on 2 pi, I'm adding on 6 pi over 3 for a common denominator. 4 pi over 3 plus 6 pi over 3 is a 10 pi over 3. And adding 6 pi over 3 to this 5 pi over 3 to get it second time around gives me an 11 pi over 3. So those are the 4 angles from 0 to 4 pi to which 2 theta would equal negative root 3 over 2. Now we just have to solve for theta. So this is like the same as dividing by 2, but notice you have a bunch of fractions over here. So if I multiply by 1/2, that's going to go away, which means I can multiply this by 1/2. Well, if I have a 1/2, that gives me 4 pi over 6. I can reduce that or cancel the 2's with the 4 and give me a 2 pi over 3. Multiply by 1/2 on my second angle, a 1 over a 2. Nothing can cancel with the 2 and the 5, so that means I end up with a 5 pi over 6. Likewise with the 10 pi over 3, multiply by 1/2 gives me 10 pi over 6. When I reduce, gives me a 5 pi over 3. And then the last one, we would multiply by 1/2. That would just multiply the denominator by 2, which would give me 11 pi over 6. So this is my final answer for theta. If the delay will hurry. Okay, so let me finish this up. That should be a theta. didn't take it, and then this should be a 6, just to clean it up. Okay, so that's a quick little review of trigonometric equations. Make sure you can do that. All right, last page in this section. It's a lot easier to get through this material. It's not as long, but there's a lot in here. So, one function gives all 6. Given the following information, evaluate the other 5 trig functions. So I'm given the cosine is -4/5. This is where your Pythagorean theorem, having triangles set up in the coordinate plane, is very important. So here I'm between pi over 2 and pi. Here's 0, there's pi over 2, here's pi. So I'm in the second quadrant. I'm just going to create a right triangle where my perpendiculars drop to the x-axis. Here's going to be our theta that we're referencing as a reference angle. And so cosine to be -4/5. That's the adjacent over the hypotenuse. So adjacent is this side, hypotenuse is this side. Now, one of them has to be negative. Remember, a radius is never negative, so that one's always positive. It has to be the ones on the axes or the one in the vertical distance. Now, you can use Pythagorean theorem here, a squared plus -4 squared equals 5 squared. But if you are familiar with Pythagorean triples, it'll be very, very easy for you to find that this side is 3. So again, you could go a squared plus a -4 squared equals a 5 squared. This gives you 16. When you subtract it from 25 is a 9. Therefore, a squared equals 9. Square root both sides, a equals 3. So from that, we can find the other 5 trig functions, okay? I like to do sine of theta, cosine of theta, tangent of theta. What's the reciprocal of sine? It's cosecant of theta. Reciprocal of cosine is secant of theta, and cotangent of theta. So this one is already given to us. That's -4/5. So according to that theta, what's the sine? The sine is the opposite over the hypotenuse, so that would be a 3/5. Sine is positive in that quadrant, so that's good. Tangent is going to be the opposite over the adjacent. Opposite over adjacent is -3/4, and it's very nice from here on out. If you've got it, we just have to do reciprocals. So the reciprocal of sine is cosecant. That would give me 5/3. Just flip the fraction. This gives me -5/4, and this gives me -4/3, and voila, you are complete. Okay. All right, and the last review that I have, I'm just giving you kind of some graphs here of trigonometric functions. There's a lot we have to deal with. If we have to go more in depth, we will do that later. But here's just a reminder of some of the graphs. Trigonometric functions are what we call periodic functions. They're cyclic. That means they keep going over and they repeat patterns. Their values repeat over every interval of some fixed length, which is called the period of the function. And there are 2 different types, basically 2 categories. There are 4 that have a period of 2 pi and 2 that have a period of pi. Those that have a period of 2 pi are going to be sine and cosine, and they're reciprocal. So cosecant and secant. As you see down here in this graph, here is one period of sine. 1, 2, bam, right there, from 0 to 2 pi. Here is one complete cosecant graph. Okay, kind of look like parabolas, one on going up, one going down. Here is the next period that gets me to 4 pi, and here's another period of cosecant. Same way here with cosine. Here is one period of cosine, and notice we have one period of secant with that. So in this case, the parabola on this side's kind of broken up according to the period. And then the other 2 functions that we have with a period of pi are then the last 2, which are tangent and cotangent. And they kind of take on the form, it almost looks like an x cubed on their graph as a reminder of that. So notice here from, let's see, this actually is one complete period of tangent. It kind of, if I end up having this over here at -pi/2, this gives me a complete period around the origin. And for every pi after that, it works. And so one of the asymptotes is at pi/2, -pi/2, 3 pi/2. The asymptotes for cotangent, it is just a reflection over the x-axis of tangent, okay? So we end up kind of looking at a negative x cubed, and it goes from 0 to pi, from pi to 2 pi, 2 pi to 3 pi, and that represents each one a period of cotangent. So as a reminder, please make sure that you have that. Now, For a general function that we have for our trig function, we're going to say y equals a, and I'm going to use sine, but you can use any of the others, b times theta minus c plus d. Okay? The amplitude is how high or low that my graph goes, okay? And that is represented by the number out front. If it's 3, that means it's going to go up here to 3, back down to 0, down to -3, and back to 0 without any other shifting. The horizontal shift is c, and this should be familiar that with our transformations out of section 1.2, remember you take the opposite of what you're looking at inside there, and that gives you that horizontal shift. Vertical shift is always that plus or minus number at the end. We take that sign as is. And the period, how much we go across here from 0 to 2 pi or 0 to pi, whatever the case may be for one cycle. The period for sine and cosine is 2 pi over b. Okay? So that is all the things that I can constitute with these 4 trig functions here. And for tangent and cotangent, everything is just the same. If I have a generic equation where I have tangent and cotangent here, all that's going to be the same except for that period. That period, remember, every pi has a new cycle. Then that would be just pi over b to determine that period. Okay? All right, so let's see if we can throw a couple graphs on these equations that we have here. Cosine and sine. We are going to have f of x is equal to 2 cosine of 4x. Here's my amplitude, so that means that for my graph, I'm going to go maximum of 2 and minimum of -2. The only other thing, there's no horizontal shift, nothing plus or minus inside with the x, nothing plus or minus at the end, so there's no horizontal or vertical shift. That means, though, that I do have a period change. Now, cosine has a period of 2 pi originally. When I divide that by b, that gets me a new period of pi over 2. So in every pi over 2, I'm going to have a new cycle of cosine, okay? So I'm going to kind of do 2 cycles here. I'm going to let this be my pi over 2. Then I'm going to finish off another one by the next pi over 2, which would end at pi. And so cosine of 0 originally is 1, but if I have the 2 out front, that means I'm going to start here on the y-axis up, not at 0. I'm going to start at the maximum amplitude. And that means, let's see if we can put this on here. If I divide by 2, or multiply by half, that means that this is going to be pi over 4. And this part right here, half of 1/4 is an 8, so this is going to be pi over 8. This is 2 pi over 8. This would be 3 pi over 8. And this is my 4 pi over 8, okay? So that would be my in-betweens. Now, changing the color so you can see that, I would end up having this point comes down to 0, goes down to my minimum, back to 0, and back at 1. So if I do that here with these, then we're going to come down to 0, down here, down here. These would be at every pi over 8. So this is going to be 8 pi over 8, which we can write as pi. This is 7 pi over 8. This is 6 pi over 8, which is the same as 3 pi over 4. And this would be 5 pi over 8. Okay? So my graph is going to look something like that. And that's just 2 periods, okay? Basically, from the original, there would be 4 of those all in one. That 4 is helpful in knowing that. Okay, let's do sine. Sine is one that starts originally at 0, 0. So if you look up here, starts at 0, 0, goes up to 1, down to -1, and back up if we have an amplitude of 1. But this time we do not. We have an amplitude of 3, so that means I'm going to go max of 3 and minimum of 3, of -3, excuse me. 1, 2, 3. So there's 3 and -3. Now notice I have a negative this time out front. That's going to be a reflection over the x-axis. So instead of starting at 0, 0 and going up and then down and then back up, we're going to start and go down and then up and then back down, okay? Now, there's 2 other things that we have in here. We have a +1, which is a vertical shift by 1. So I'm going to move that up 1 and just kind of draw a dashed line if that helps you. You don't have to. That means I'm going to have to max 1 more up to get my amplitude of 3. And we also have here, we can write that x over 2 is the same as 1/2 x, therefore 1/2 is equal to my b. To find the period of this new graph, we have to take 2 pi over that 1/2. And if I divide by 1/2, that's the same as multiplying by 2. So this would be 4 pi would be 1 cycle. So in 1 cycle, I'm going to have 4 pi. Half of that's going to be 2 pi. Half of that's going to be pi. So for every pi, I have a significant point. So I would have 3 pi, 5 pi, 6 pi, 7 pi, 8 pi to get my second period here. All right, so this is kind of like my new axis coming up. So we're going to start at 0, 0. Instead of going up 3, we're going to go down 3. So 1, 2, 3 would be here at -2. Come back to 0, or that new axis zeroed point. Then we're going to come up to 4, back down to our 0. And I continue that pattern for the rest of my graph. And again, there's a delay. Try to get the best you can. Trying to do this blind sometimes. I'm going to finish it off by getting down here at 8 pi. So again, that's 2 cycles of that sine curve, but you can see here that depending on the directions they give you, you can do 1 cycle. They may end up doing multiple ones, so that's why I did multiple ones as well. All right, very good. So that is our review of trig. So if you were having some difficulties with that, please come see me. Hopefully not. Hopefully that's a good review of, oh yeah, I can do that. Trig is a little different beast than some algebra functions, but it is doable and we will hit some of those. So come back for chapter 2. This again is the end of chapter 1 and end of our review, and we're going to head into chapter 2 and start some calculus. Until next time.